All right, so this is the formula sheet that you will be allowed to use. This stuff at the beginning, these chapters are pretty much things already you've done, and then up here we have a normal distribution, and for sampling distributions, which is what we've been looking at, so you have the mean of your sample, but you want to know where does your sample fall in the distribution instead of a person within a population. The mean is your expected mean is the mean of the population. Your expected proportion is the proportion of the population. For standard deviation of a sampling distribution, so this is if you're talking about where is the sample in a distribution instead of a person, you take the standard deviation of the population and you divide by the square root of the sample size. For sample proportion, if I roll a die 100 times and 20 times I get a 1, then the sampling proportion of ones is 20 over 100. The standard deviation of a sampling distribution for a proportion is the square root of this p times 1 minus p all over n. Okay, so then confidence intervals. This is the little formula that kept showing up that I kept repeating to try to help you remember. For proportion, this you'll recognize now as the standard deviation up here, and so it's expected value plus or minus z times the standard error. That's what it always is. P plus or minus z times the standard error, or x bar plus or minus z times the standard error. You always start with your expected value, which is a proportion or a mean, and then add or subtract the z-score times the standard error. Standard error for proportion is this one. Standard error for a mean is this one. So this is confidence interval for mean, because then it's t or z for the sample. The reason this is t, so you could have had still z here and sigma there. This is if we don't have sigma. So we don't have the standard deviation of the population, then we use t, the t table, assuming our sample is small. Because we're not only approximating now the mean, but we're also approximating the standard error. So if you approximate, twice like that, then you'd have to have kind of confidence going in two directions. So we just kind of fluff up the available error a little bit. For t, the degrees of freedom is n minus 1. So whatever your sample size is, subtract 1. You never ever go up. Like if your sample size is 100, you look at the table. The tables are on here too. So t, I guess I need to look at this more. There's t. So if we want, say, 90% confidence, the reason that this said alpha over 2, and it's always saying alpha over 2 for confidence intervals, is because I'm going, this crazy pen keeps, okay, it's so annoying. We're looking for, we start in the middle and we go either direction on the x-axis here, the same amount, so that up here is whatever value we wanted. So these together add up to alpha. So a single tail is alpha over 2 because it's split in half. Both of our charts give us only a single tail. Z gives us a left tail, T gives us a right tail, but either way, they give us one tail. So if we want to have alpha total on both tails, then we look up the one that gives us alpha over 2. So if we wanted, say, 95% confidence, then we have 2.5 in the tail. So we would look here on the T table, it's the right-hand tail that's at the top. So up here, if we were doing 95% confidence, then we take half of the 0.05 as far as the tail. If we had 100 people in our sample, we can't use 100 because our degrees of freedom are 99. So we would drop down to 90. And we're here, and we'd use 1.987 as our t value for that. Okay, so everything about confidence intervals is here in Chapter 9. Hypothesis testing stuff is here to find the z-score, the t-score, or the chi-squared score. Okay. And then I don't think you need to go higher than that. There was one thing I skipped, though, I think, back in confidence. I kept showing you guys how to start from here to lead to how many do I need to control my error. That's actually here, so you don't need to memorize that. Z for alpha over 2, so that's the same as before. S is the standard deviation. E is the error that you're allowing, so I want to be within 12, then E is 12. You square it, and then always round up, because you can't have a part of a person, but if you lose that part of a person, then you don't have a big enough sample anymore, so you just get the whole person. Okay, so these are the formulas that are all here. Let me see if we can more quickly then kind of go through these. You have access to these, so if it's stuff I think's been addressed, then I'll just skip over it the moment. So the 1.645, 1.96, and 2.575 came from tables. Oh, there it is. Okay, so we're going to go to the Z table real quick. Here's the Z table. If I want 90% confidence, then alpha is 10%. Alpha is what's left. So I have 10% over 2, so 0.05. So I look here on the T table, remember we looked for the tail up here. On the Z table, we're looking for the tail in here. So I'm looking for 0.05. And I have these two, 0.0505 and 0.0495. And that's between negative 1.64 and negative 1.65. So splitting the difference, we've got 1.645. The negative doesn't matter because we're adding and subtracting anyway. For 95% confidence, alpha is 0.05, so that's what's left. So I'm looking for half of that, 0.025. 0.025 is right here. So negative 1.96. So 1.96. For 99% confidence, you have alpha 0.01. Half of 0.01 is 0.005. So 0.005. There's 0.0049 and 0.0051. So it's right between these two. Negative 2.57 and 2.58. So 2.575. Just splitting the difference there on those as well. That's where those three come from. Anytime it's Z, of course, it'll be those. So if you have a great memory, you can go ahead and memorize them. You start with the mean. Add or subtract Z for alpha over 2, which is one of these three, times standard deviation over root 17. In your formula sheet, going to confidence intervals, it is right here, x bar 2.464, plus or minus, T for alpha over 2, in our case we're using Z right now because we have the population standard deviation. So Z for alpha over 2 times S, in this case sigma, 0.02 divided by root 17. And skipping down. These are good to look through if you haven't yet. Now we have it where we do not have the population standard deviation. So we would use T and we would use S. The reason on this sheet he does not is to show you how it fails. Because once you approximate that SD, like I said, you need to kind of pad your errors so that you're safe. It's always better safe than sorry. So right here or here somewhere, we start having the T-chart. Okay, here we are. So we take the same 2.464 right there, plus T for alpha over 2 is these 3, times S, the standard deviation, is the 0.018, divided by root 17. And then it's 2.464 plus or minus all that junk multiplied together right there is 0.008. So this was just put into a calculator and found to be 0.008. And that T came from, we have 17 people, pennies, so our degrees of freedom are 6. So we're on this row. If we look for 90% confidence, again, alpha is 0.1, so alpha over 2 is 0.05. So 0.05, 1.9, sorry, I went to the wrong one. 16, not 6. That row, 0.05, 1.746, 95% confidence, so alpha is 0.05, half of it's 0.025, so 2120, and then 99%, 0.01, so 0.005, and 2.921 is the critical t-value that makes this interval. Okay, so sample size. So now this person wants to be within 0.005. They want their confidence interval error to be no more than 0.005. So the error is how far you go in each direction, and we don't want to go more than 0.05 in either direction. So this error, all this stuff, the t times the s divided by root 17, we want that to be no more than 0.005. So we could work that all through, or we can go get this formula here. Maybe I should cut off some of these for you guys so it's less confusing. Right here. So we take z for alpha over 2, 99% confidence, 99% confidence, so 0.005, and that was the 2, 0, 0. Right here, 2.575. Okay, so back up here. 2.575 times the standard error divided by the error, and then all of that squared. .575 times the standard error was 0.018, and then we divide by 0.005, the error, and then square it. So we had z times s divided by e, and then all of that squared. So z times s divided by error squared. You can't have 85.93 people, and you have to have that person to make it work, so we get 86 for that. Okay, to put the confidence interval in the calculator, there are two possibilities. You'll either have a list, or you'll have already the expected and the standard deviation. So on here, okay, I'm going to get a list. 93. Okay, so I put these all in. Go back up, hit menu, statistics. Stat calculations I would only go to if I wanted, right as far as these topics, if I wanted to get mean and standard deviation of something. Confidence intervals for confidence intervals and tests for hypothesis tests. We're in confidence intervals right now. We only have 11 things and we do not have the population standard deviation. So we're going to do T. And our input method is data because I put the list in. I do want 95% confidence, so now the confidence interval is 76.9 to 88.3, which means I'm 95% confident that the actual average length of these animated films is between 76.9 and 88.3 minutes. The margin of error is 5.7 because I went 5.7 in each direction. The interval itself is 11.4 because it is two errors. It starts from the middle, goes error to the right, error to the left. Vice versa, I guess, if you want to go lower, upper. So because this interval is 11.4, I could have already told you that the margin of error was 5.7 because it goes the margin of error in each direction, so it's twice it. Okay, for this one, we have a sample size 5, and we are given the average, we're given the standard deviation, we are not given the list. We do not know each month's result. All we know is the average and the standard deviation. So now, I'm still going to go to list because that's where it kind of spits all this stuff out. If you accidentally click in that box so that that cursor is flashing, when you go to menu, you won't be able to do stuff. So when you go, just click it till it's blue and then go menu, statistics, confidence intervals, T interval again, sample size 5, don't know the population standard deviation, but this time I'm going to do stats, because I do know the mean and the standard deviation already. The mean is 28, the standard deviation is 3, sample size is 5 because each member of the population is a month. And this time I wanted 0.9, 0. You don't have to put the 0, but just so it's clear to you that I'm doing 90% confidence there. So now I am 90% confident that the true average number of mail carriers bitten by dogs each month is between 25.14 and 30.86. So note that is 5.73 range, and so 2.86 in either direction. So that's the margin of error. The margin of error is the t-score times the standard deviation divided by root n. Always. Okay, so this one we want to solve for n, and if we looked on our formula sheet, we have this z s over e all squared. So I guess I've already done this one on this calculator. Interesting. Okay, well, I don't know how to clear this then. So Anyway, we want to find 90% confident would be 1.645, which you can get off the chart if you don't remember looking up 0.05. 1.645 times the standard error, standard deviation, divided by the limit, 25. $27.7097, so 28 people is what we need for this one.